Fourier uncertainty and band limited function. Please, Colonel. Emanuel,
right.
can you? Yeah.
Yes, I can hear you guys. I hope you can all hear me. So I'm sorry that you can't see me. So thanks a lot for the invitation to speak in your seminar this afternoon for you. I want to be brief. So the title is, as you see here, Fourier uncertainty and band limited functions. So I can only see the slides here in front of me. So please, from time to time, somebody speak and say something. So I just hear that you guys are still there and I haven't lost the connection, okay? Okay, so this is the title. And I just want to talk to you briefly this afternoon about some, very classical stuff about one of the most classical operators in analysis. This is the Fourier transform. So everybody has had some contact with the Fourier transform before, but just so we are on the same page, let me remind you that if I give you an integrable function f, the Fourier transform f hat is just the integral over r of this exponential e to the minus 2 pi I x c, f of x dx. And this is just, let's say, in one dimension. I just say this so we are clear on the normalization. I use the Fourier transform with the minus 2 pi I. And I want to say, this is one of the most famous objects when one studies harmonic analysis, which is the study of oscillation, right? Oscillatory phenomena in mathematics. So this sort of operator encodes the many oscillatory phenomena that we study in analysis and in other fields. It's essentially used to decompose a function into simpler functions, right? Like you do for trigonometric series when you write a periodic function as a sum of sines and cosines. You do this in general with the Fourier transform. And there's this philosophy of the Fourier uncertainty principle, that is essentially any sort of statement that tells you that you cannot have an unrestricted control of a function and its Fourier transform simultaneously, right? What do I mean by this? Well, if I give you the function f, then the Fourier transform is completely determined, right? You cannot give me a function f and ask the Fourier transform to be something it is not. So if I give you the full f, then the Fourier transform is completely determined. But, I can give just f partially, I can give f partially, and I can give the Fourier transform partially, and I can ask if these conditions are, let's say, compatible. They may or may not be. So if I give you too much information about the function and about its Fourier transform, it might be the case that the only function that verifies your hypothesis is the zero function, right? And this is in the spirit of classical uncertainty principles that you see in the literature out there. Like, for example, you have these classical uncertainty principles that say that if the function and the Fourier transform decay faster than a Gaussian, then the function itself must be a Gaussian, right? And you have these statements in physics appearing in quantum physics saying that you cannot control at the same time, the position and the velocity of a particle. This is essentially to say that you cannot concentrate the function f and the Fourier transform f hat in a compact set. You cannot have both f and f hat compactly supported, for example. That's another example of an uncertainty principle. So any statement in the literature that gives you some sort of restrictions on the use of the function and the Fourier transform is understood. It's called an uncertainty principle. And what I want to talk to you today about, it's some instances of this phenomenon. So I'll divide my talk into three parts, and I put here the slides of the Star Wars to have a little bit of a trilogy, the beginning, the middle, and the end of my story. So I have some alternative titles for this talk that I was considering, but I chose for the the most, let's say, orderly one. But the alternative titles could be, for example, this one. Why should you care about this function written on the board? Or the other alternative title, as you'll understand along my talk, is the moving company project. So this is a story about many mathematical and non-mathematical values that I particularly like, that I would like to share with you. The first part, so our story, at least my story today, starts when I went to a conference in Canada in 2015. This is the Banff International Research Station. And I went to a conference there, and the conference was called the Geometry, Algebra, and Analysis of Algebraic Numbers. In this talk, in this conference, this was in 2015, I was studying some sort of extremal problems in harmonic analysis. And one of the, let's say, key results in analysis that is important for what I'm going to talk to you today is this nice theorem of Paley and Wiener, which is it's a bridge that connects harmonic analysis and complex analysis. It says the following. So this, if you want to take one thing from this lecture, if there are graduate students attending, if you want to take one thing home, this is perhaps the theorem that you want to remember here, which is going to be important for you in many situations. But it says that if I give you a function in L2 of R, right, the following things are equivalent. Well, its Fourier transform is compactly supported. It's equivalent to the fact that the original function f, which was originally just in L2, is much more than that. It can be extended to an entire function of order 1, and it verifies, it grows like this. It grows like modulus of f of z grows like e to the 2 pi delta modulus of z. Right? So an entire function of order 1 is a function that grows like e to the az for some a, and the a here is related to the size of the support of the Fourier transform. So if the Fourier transform has support in the interval minus delta delta, this means that your original function grows at most like e to the 2 pi delta modulus of z. So in this sense, functions that have Fourier transform compactly supported, that are also called band-limited functions, these functions are essentially functions of a complex variable of order 1 that have exponential growth. So these are called functions of exponential type. Okay, this is the theorem of Paley and Wiener, and here are the pictures of Paley and Wiener. As you can see from the picture, from the subscript in the picture, I put here that Paley, he died very young. He did amazing things in harmonic analysis, but he died just at the age of 26. He was just 26 years old when he died. And I remember, so this is kind of the theorem that I presented in this conference. This is the paper that I talked about. So I was working on in this project with my collaborator Friedrich Littmann from North Dakota in the US. And this is about monotone extremal functions. So this was a problem about approximating real valued functions. In this case, the signum function, the function that is -1 on the negative axis and +1 in the positive axis. I wanted to approximate this function by functions of exponential type, okay, by band-limited functions. So this is kind of a classical problem in approximation theory. How do you approximate genetic functions by functions with a good Fourier transform, with a compactly supported Fourier transform? In other words, a band-limited function. And sometimes you ask for particular applications that this approximation is not only an approximation, let's say, that crosses over the original function, but it could be an approximation that lies above. So in this sense, we call a majorant, or you may want an approximation that lies completely below. In this case, we call a minorant. So this is important to generate some sort of inequalities, if you want, for your application. So The problem of majorizing and minorizing this signum function dates back to almost 90 years ago, studied by Berling and Zellberg, you know, with applications to inequalities in analysis and number theory. And this is a well-known and solved problem. There is, if I prescribe the size of the support of the Fourier transform, there's just one function that majorizes the signum, minorizes, and another one that minorizes the signum with that prescribed support. And of course, I have to tell you, what do I want to optimize? I want a majorant that optimizes the area between the majorant and the function. In other words, the integral of the difference between the majorant and the function. So in this conference, I discussed a little bit about a variant on this problem, which is when you require that your majorant has some sort of monotonicity properties. So I wanted to find a function that has, let's read this theorem together. Let f be a function which has exponential type 2 pi. So you want a function that is real on the real axis, but it's an entire function of exponential type 2 pi. Then you can say by the Pelley-Wiener theorem that roughly this function has Fourier transform supported in -1, 1. I want the function to be above the signum. And remember, signum of x is just 1 when x is positive and -1 when x is negative. And I want, but I want my function to be non-decreasing on the negative axis and non-increasing on the positive axis. So I want my function to grow and then to come back, to come down, to be increasing and then decreasing, just a little bump. So under these conditions, for example, you can show that the best that you can do for the difference between f and signum, for the integral of the difference, this distance, is 2. You cannot beat the number 2. So the integral of f minus signum is at least 2. And there is a unique extremizer for this problem, which is this function here written on the board, m of x. That's the best majorant that verifies these optimality problems. This has had an application, and I just wanted to mention to you this application to the so-called Hilbert's inequality. So there are a chain of inequalities that are known sometimes as Hilbert's inequalities. These are inequalities for certain Hermitian forms, right? For example, if I give you complex numbers a1 up to an, and you can always take the sum of an bar divided by m minus n, and the modulus of this number will lose to the sum of the squares of the numbers, the little L2 norm, times a constant, pi in front. And the nice thing is that the constant pi here is sharp. You cannot put a smaller constant in front of this thing. There was a generalization of this theorem by Montgomery and Vaughan in 1974 with some applications to number theory in mind, where they replaced the bottom sequence that we had m minus n. They put numbers, generic numbers, lambda m and lambda n. So the statement is now as follows. I give you a sequence of lambda 1, lambda 2, up to lambda n, a set of these distinct real numbers. And I define for each of these numbers, lambda I, the spacing, delta I, which is kind of the spacing that each of these guys have. So delta n is the minimum of the lambda n minus lambda m for other m's. So it's around each guy, lambda n, you can put a little ball of radius delta n, and you will have no other point. Then, given this set of numbers, if I give you a sequence of complex numbers, a1, an, then you get a sum like this. Sum of an bar, lambda n minus lambda n, loses to now a little L2 weighted norm, sum of the squares of the numbers an, but divided by this delta n, times a constant. This is an inequality that was proved in 1974. So Montgomery and Vaughan originally proved this with the constant 3/2 of pi. This was improved about 10 years later by Preisman, who got about 1.31 pi, about 4/3 of pi. We gave a new proof with the result that I showed you in the previous slide with these extremal functions with a slightly worse constant, 2 pi. But the advantage is that this proof is very simple and it uses Fourier analysis as opposed to the first two proofs here that use more, spectral theory, a little bit of linear algebra, because you can always search for the largest eigenvalue of a certain Hermitian matrix here and try to go in that direction. And it's a conjecture, that has 50 years old, that this constant should actually be pi. The sharp constant in this inequality should be actually pi. But it's an open problem. Okay. Are you guys still there? Can I hear some voices?
Yes, very well. It's going good.
Okay. So let me continue. So in this conference, a nice memory that I have is we took a little stroll to the cemetery. This is the Banff International Station in a little city in the middle of Canada, in the Rocky Mountains. And if you take a stroll of if you take a walk 15 minutes away, you are in the old Banff Cemetery. And you know who is buried in there? It's actually Raymond Paley. So Paley, as I told you, died at the age of 26. He was British, but he died on a ski accident in the Rocky Mountains, and so he was buried there. So this is a picture that I took in the tomb of Paley. This is me, and this is my advisor, Jeff Waller, from the University of Texas. This is a picture that I'm very fond of, and whenever I look at this picture, I remember of this picture from the movie Back to the Future that shows a student, a scientist, and something important in between, That's my version of, this is my Back to the Future picture. Anyway, in this walk, so my advisor was there at this conference with me, and he asked me, we discussed about the following problem. This is called the monotone 1 delta problem. So there is a classical problem in approximation theory when you want to construct a non-negative function on the real line with Fourier transform compactly supported, let's say in the interval -1, 1, but the value of the function at the origin should be at least 1. So you want a non-negative function such that at the origin it's at least 1, but the Fourier transform is supported in -1, 1. And you want to minimize the integral of your function. And just so we are clear, what lies behind a problem like this is the uncertainty principle, right? Because you can say, well, Emanuel, you want a non-negative function, but at 0 the function should be 1. So why can't you make the function very, very, very small, and just at 0 you go up a little bit and you make it very, very, very small, so you can make the area as small as you want. So if you want to minimize the integral of f. The reason is that you cannot do this because you would be concentrating the mass of the function too much around the origin. And the mass of the Fourier transform, since it's compactly supported, is already concentrated in the interval -1, 1. So you cannot concentrate too much the mass of the function and the mass of the Fourier transform around the origin. That's an example of an uncertainty principle. So this problem that I just described to you, problem of constructing a non-negative function such that the value at 0 is 1, the Fourier transform is supported in a prescribed interval, say -1, 1, and you want to minimize the integral of this function. This is a classical problem in approximation theory called the 1 delta problem. And the answer is unique. There is just one function, and it's this so-called Fourier kernel, sine pi x over pi x squared. That's the best function for this problem. Now, we discussed a variant of this, when we were walking in this conference. I discussed with my advisor that he asked me the following question, because these two problems of majorizing, the delta at the origin, let's say, and the signum function have been considered many, many years before. And so we're just considering a variation of this measurement of the signal where we introduced some monotonicity constraints, right? We wanted the function to be increasing and then decreasing. And these monotonicity constraints were useful to prove these Hilbert type inequalities. So he asked me the following thing, well, you kind of found the extremal solution for the signal problem with the monotonicity constraints, which seems to be a harder problem. Can you solve the same problem for the delta function? In other words, can you actually construct a non-negative function on the real line that at 0 at origin it's above 1, is at least 1, but the function is radial decreasing? So what's the best radial decreasing function that is non-negative, at 0 is at least 1, and has the Fourier transform compactly supported? So here I am writing the problem in several variables. So we want to find a function f from Rd to R, which is radial and non-negative, of exponential type 2 pi. This you can understand, just ask that the Fourier transform is supported in a unit ball, such that f of 0 is at least 1 and the integral of f is minimum. So I thought, well, this should be a simpler problem than the one I can solve. And if you work out this problem, it boils down to solving the following seemingly innocent problem in dimension 1. So I give you a function g of exponential type pi with such that the integral of g squared times x dx is 1. So this is a function with Fourier transform supported in -half-half with this normalization. And then I ask you to find the minimal value of g of x squared with a different weight. Let's say x to the d plus 1, where d is the dimension. So if you want to solve this first problem in dimension d, you would have to solve this one-dimensional problem with the weight d plus 1. This seems very innocent. Well, you get some L2 normalized function here to be 1, and you want to find the minimum of another normalization of the L2 norm of the function, another L2 weighted norm. And at the moment, I could only solve this problem for dimension d equals 2. So when you have here the weight 3. Well, and I'll tell you in a moment why this is not so easy as it seems. Well, I tried this problem a little bit, and it laid, as I said, I could only solve it in this one particular dimension 2. And I tried over the years, but without success. And then 7 years later, I came back to this problem in the following situation. So you fast forward from 2015 to 2022. Here we are at ICTP in Trieste. Some of your colleagues might have visited. I have currently one postdoc here from India, Mithun Das, working with me. So and get some visitors from India from time to time here. Inclusive, our director is actually also from India. And at this moment, our analysis group here was a bit bigger, in the sense that I had 2 postdocs, Christian and Andrea. I had 1 graduate student, this is Antonio Pedro, and we had 3 visitors here at the time, visiting for 2 months. So we were a group of 7 people, all in harmonic analysis, and these 7 people started to talk to each other and about different projects, and put different appointments and conversations going on. And at some moment I kind of proposed to them, hey guys, we all work in somewhat similar things. Why don't we all, instead of having multiple projects going on here between every pair or triple of people, why don't we sit together in a room, we discuss some problems, and we work for 2 months heavily on one problem, everybody. So we did this, everybody liked the idea, and we sat in a room and we discussed, everybody kind of proposed some problems, and I kind of proposed this old one that I had thought about 7 years before, but never actually managed to finish it. And so this is kind of a toy model for my problem. If I give you a function in L2, so this is a very simple problem. If I give a function in L2, what the Fourier transform, and we are in one dimension, L2 of R, Fourier transform compactly supported, let's say in the interval minus half-half. I want you to find the sharp form of this inequality. The L2 norm of f being bounded by the integral of f squared times x squared dx. Again, why is this inequality true to start with? Why is this inequality true? Well, if you say that the left-hand side is 1, if you normalize the L2 norm of the function to be 1, why can't you make the right-hand side very, very small to break this inequality? The reason is to make, if you have, let's say, L2 mass 1 for f, if you want to make the right-hand side small, since you're multiplying by x squared, you would have to concentrate the mass near the origin. But again, you cannot concentrate the mass of f too much near the origin because the mass of f hat is already concentrated near the origin. And again, this is the philosophy of the uncertainty principle behind you. You cannot concentrate both the mass of f and f hat in some sense near the origin. So this is why an inequality like this is actually true. There is a threshold on how much you can concentrate the mass of f near the origin. And the question is, what is the sharp constant that you can put here? And this is the only proof that I want to give to you today. It's just a short proof of this toy model problem. And it's very simple. Well, if a function f in L2 has Fourier transform supported in the unit interval minus half-half, you might know from this theory of, sampling and interpolation of functions that you can reconstruct the function f just based in some samplings at the integers or at any translate of the integers, right? This goes also back to Paley and Wiener and so on. But then the L2 norm of f is just the sum of the values of f at the translate of the integers. Here I'm taking n plus a half, the square. Okay, you can prove this fact. And then if you believe in this fact, well, then why am I taking the translate 1/2 here? Because I want to get as far as possible from the origin. You multiply by 4 and divide by 4. I didn't do anything in this line. And then in the second line, there is an inequality here where I'm changing this 1/4 by n plus half square. When n is 0, I get 1/4. When n is minus 1, I get 1/4. And for all the other n integers, I get something bigger. And why do I do this? Well, because then this is the norm of, this is f of a number times this number squared. So this is the norm of the function x times f of x, which is actually this norm here on the right-hand side. That still has, if I multiply my function by a polynomial, I don't change the support of the Fourier transform. So this function is still supported in the Fourier transform is still supported in the interval minus half-half, and I can apply the same interpolation formula to go back to the L2 norm. So you have an inequality here. The L2 norm of f loses to 4 times the L2 norm of x times f. Well, and this inequality that you generate here can actually be attained, How is it attained? Well, you must have several coefficients of this function f being 0, unless when n here is 0 or minus 1, because then this is when equality happens. And then you can find that, this is the formula that recovers the function by the samplings at the integers plus a half. So you have lots of these coefficients will be 0, unless when n is 0 or minus 1. So the equality in this case will hold if and only if this is your function. I just combined two signs here and became a cosine. So the function is cosine pi x divided by x squared minus 1/4. This is the function that is optimal for this problem. And as a matter of fact, I know that you guys are also interested in PDEs. So this is kind of connected if you don't want to look at things with the Fourier transform, if you want to look at this inequality from the Fourier transform side, well, the L2 norm of the function is the same L2 norm of the Fourier transform. And then this guy, multiplication by x on the side of the Fourier transform becomes derivative. So on the Fourier transform side, this is the same as bounding a function, the L2 norm of a function by the L2 norm of the derivative. This is one basic example of what is called Poincaré inequalities, right? And there are many things in the literature. Here's just a post from Math Overflow where how you can find the sharp constant for the Poincaré inequalities. Here, remember, the Fourier transforms are supported in the unit interval. So I want to estimate the constant, the sharp constant for Poincaré inequalities for functions that lie in a Sobolev space of an interval. And the analogus of this one, of multiplication by x, is the classical Poincaré inequality that bounds the L2 norm of the function by the L2 norm of the first derivative. And you can argue with the Sturm-Liouville, finding the first eigenvalue of an associated Sturm-Liouville problem, and you find the same constant that we found there. Well, once you put the proper normalization into play. Okay, this is a post by Giuseppe Negro, which I think it was in a conference with you guys in Bangalore last year or 2 years ago. I just made this, found this post online of him 10 years ago just to have a laugh with him. Anyway, so this was the problem that I proposed to our friends at ICTP when we were together. Well, I know how to find the sharp inequalities when this was x2, but you can change the x2 by, x to the 4, x to the 6, x to the 8. For example, how do you find, give me a function f in L2, support of the Fourier transform in minus half. How do you find the sharp inequalities if I want to bound the L2 norm by, L2 norm with different weights? Again, the reason that these inequalities are indeed true, it's because of the uncertainty principle. You cannot concentrate the mass of f too much around the origin, but I'm interested in finding the sharp forms of these inequalities. And we started to discuss, the techniques that I showed to you for the proof when you have x squared here on the right-hand side do not apply to a larger exponent because you cannot make the equality happen, okay? So you actually need some new tools. And after we discussed a little bit, we kind of made some progress in, we broke a barrier and we could solve the problem with the x to the 4. And this is when I noticed that, okay, we do have something here that we can move on, right? So this is how our project started, with solving the next simplest case, and then we could see a little bit of the way ahead. This was where I was stuck a few years before. So it's very nice in mathematics when you start discussing with your friends and you make a little bit of progress in a problem that you've been thinking about, but we all have this feeling that, okay, here I'm actually getting to something new. I know this is gonna give me something. I don't know what's going to be the final shape of this, but I know that we are onto something potentially interesting. So I kind of had this feeling when we started and we solved this first one. So just as for the sake of curiosity, for example, if I give you a function in L2 with the Fourier transform compactly supported in the interval minus half, you can ask for the sharp form of this inequality here, bounding the L2 norm of f by the L2 norm of f times x to the 6th dx. And the way that I have written this on the board, you might object. You might say that one thing is missing, which is the constant in front of the integral. But I'll tell you that no, this is not a mistake. This is an inequality that is true. And this is actually a theorem. So just one corollary of our results is this theorem, which I find it very interesting and easy to state. If I give you a function in L2, Fourier transform supported in minus half, This inequality is true. The L2 norm of f loses to the L2 norm of f times x to the 6 d6 with this x to the 6 dx with this weight. This inequality with the constant 1 is sharp, and the unique extremizer is this function here that I was kind of proposing to you as my alternative title. Okay, so it's kind of an interesting and basic inequality in analysis, which, as far as I know, it had not been observed before. This is just a picture of, you know, when those guys were here and we were doing this project together, it was a coincidence that I was moving from one apartment in Trieste to another one. So I kind of asked them to help me. And this is a picture of us moving some furniture in the downtown of Trieste in one given Saturday, May of 2022. Anyway, so just in this last minutes, let me give you what we ended up doing was something a little bit more robust. So let me give you the general outline of what we proved, and you will see that those things that I just mentioned will come out as particular cases. So the problem that we studied was formally the following. I give you an alpha bigger than -1 and a delta bigger than 0. And I consider this space H alpha, dimension D, and parameter delta. This is the Hilbert space of entire functions on D complex variables. So D is the dimension, functions from CD to C, of exponential type at most delta. Then you can see, you can think of these functions having, let's say, growth like 2 pi delta modulus of Z, or Fourier transform supported in the ball of radius little delta. So consider this space of functions. This is a vector space, but you consider the space such that this integral is finite. This integral functions are this integral on Rd of f of x squared with this weight 2 alpha plus 2 minus d dx. This is finite. This turns out to be a norm, and this is a Hilbert space of entire functions. Sometimes these are called Paley-Wiener spaces or weighted Paley-Wiener spaces, okay? Now, and then you observe that when you have parameter, alpha is just the parameter that you put in the exponent here. So the exponent is 2 alpha plus 2 minus d. D is the dimension. So if you get a parameter alpha bigger than beta, the space H alpha will be embedded in the space H beta, okay? So if something is integrable with a bigger weight, x to the alpha, it's going to be integrable against a smaller weight. These parameters are bigger than -1, just so you have integrability at the origin, okay? F is just continuous at the origin, so this weight is integrable at the origin as long as this alpha is bigger than -1. Anyway, so you have a bunch of biggest Hilbert spaces. They are embedded into one another. And the question is to find the norm of these embeddings. Okay, so we want to find the operator norm of an embedding between Hilbert spaces. So the extremal problem here, let's say for alpha bigger or equal than beta, and delta a real parameter, D a natural number, I want to find the value, which I'm calling extremal problem that depends on alpha, beta, D, and delta, which is the infimum of one of these norms divided by the other. Okay. The infimum in F belongs to the Hilbert space H alpha of the norm in this space divided by the norm in the other space. It's the norm of these embeddings. In the previous cases that I was showing to you, was the case in dimension 1 with some choices of alpha and beta that would give me the L2 norm of F against the L2 norm of F times X and so on. So the other case was just a very particular choice. Here I am in dimension D with any exponential type when any exponents alpha and beta. So we have 3 types of results. Let me prove. First of all, let me start with the easiest results. The easiest results is that, for example, the exponential type, it's you can, by a dilation argument, by some sort of change of variables, you can kind of just consider this parameter delta to be 1. So you can renormalize things and the parameter delta will come out, and you can essentially consider all the functions have exponential type 1. And this is how it comes out. So it's, okay, so that's the first easy thing to do. The second thing is that the way that we set up the problem, you can apply some radial symmetrization techniques, and you can make functions of D variables become functions of one variable in some sense. So this is the first, let's say, more important theorem, is that the same problem in dimension D that I just described to you boils down to the problem in dimension 1. That's the same value. So the proof involves a suitable radial symmetrization mechanism and an auxiliary extremal problem. So we can actually reduce that general problem in dimension D to the same problem in dimension 1. And this is where the fun begins. Also, there exists a radial extremizer for a problem. So you can use, let's say, classical techniques in analysis and calculus of variations to prove that there exists an extremizer. And that this function, which is defined as an infimum, right? So it's an infimum of something, but this is a function is actually continuous with respect to all the parameters that I have, with the parameters alpha, beta, and delta. This is a continuous function. In principle, this is not obvious because it's just defined as an infimum of something. So it's kind of obvious that it's going to be lower semi-continuous, but it's not obvious that it's going to be continuous. This requires some proof. Okay, so this first part is a little bit about qualitative properties of our constant that we want to find. Now, asymptotics. So recall that we are looking now at the same problem. So I want to fix the exponential type to be 1, and I want to fix my dimension to be 1. So I really want to find, that's almost the same setup that I was discussing with you in the beginning of the talk, right? I want to find the infimum of this norm divided by this norm, when the norm upstairs is finite. Okay, when this is finite too, because this is an embedding, and I want to find the infimum of this thing. Well, with parameters, with powers here, 2 alpha plus 1 and 2 beta plus 1. So you see that in the previous discussion, we had what? We had one of them be alpha be minus a half and beta be something that made the exponent 2, 4, or 6. So we would like to find the sharp constant in all the cases. It turns out to be a hard problem, and we cannot do this in all the cases, in all the situations. So if you cannot find the exact value, you go to the second type of question that is important, which is, can you at least tell me something about how it grows? What is the asymptotic of this value? And so this is the theorem in this part. So we can say actually some asymptotics of this constant as my parameters alpha and beta move, you know. So for example, this constant here, if you take the log, it becomes essentially 2 alpha minus beta log alpha plus log of beta over alpha. You know, this is the behavior when alpha and beta go to infinity, and this is the behavior when they go to the lower endpoint, -1, plus an error term. Okay, so if you want to know, if you fix beta and you send alpha to infinity, how does this constant grow? Well, it grows like alpha log alpha. Or if you want to consider beta and alpha moving at the same time, if you want to consider beta and alpha to be beta plus 1. So let's say if alpha minus beta is 1, this constant will blow up like 2 log alpha only. So and then you can see all sorts of possibilities coming from here. Finally, we are able to find the sharp constants, the exact constant in some cases. And the cases that we can do is when this difference between these exponents alpha and beta is an integer. Okay, this is the theorem, and it involves these so-called Bessel functions that I'm sure you are familiar with. So J nu is the classical Bessel function of order nu. And when you have these functions J nu and J nu plus 1, you multiply by suitable power of z, and you get an entire function. So this function is entire, that we call a nu, and this function is b nu, which is z to the minus nu, j nu plus 1. So these functions here, they play the role of sine and cosine. Okay, you should think of this function as being cosine and this being sine. When the parameter nu is actually minus a half, this is cosine and sine. And this function c nu plays the role of tangent. So this should be sine over cosine. So you should think of this in the classical, when the nu is minus a half, when you are with the Lebesgue measure, this would be the tangent function. But in the general case, for any parameter nu, it would just be j nu plus 1 over j nu. Okay, so here's the answer for the problem. If you want to find, let's say, if you fix a beta and you want to find the solution of your extremal problem with parameter beta plus k and beta, so when alpha is beta plus an integer, if k is 1, that's the first zero of the Bessel function with parameter beta. And if k is bigger than 2, it's the smallest positive solution of a certain determinant. You have a matrix, you have a big matrix, and the matrix is, if k is bigger than 2, you set L to be half of k, roughly. And so you construct an L by L matrix with these entries. The entry mj is just a sum of a certain root of unity times the values of this tangent at some root of unity times lambda. So the lambda is the variable. So you have a big matrix, and all the entries are certain combinations of this tangent value of the variable lambda multiplied by some roots of unity, right? So you have each entry is a function of lambda, and you construct the determinant, which will be a function of lambda, and you solve the determinant equal to 0. The smallest positive solution is the value of the sharp constant. That's as explicit as we could get the description. Well, this paper is on the archive. If somebody is interested, you can certainly check there for more details. I just want to say why this, I mean, you can say, Emanuel, this is kind of a little bit of a bad description for the sharp constant. It's the smallest solution of some equation. Well, I just want to justify to you why it's not so bad, why it's reasonable to expect that it's supposed to be as hard as this. Okay? But first, let me just give you an example. When you make k equals 3, in our case here, so the L will be the integer part of 3 over 2, L will be 1. So a 1 by 1 matrix is just one entry, it's just one equation. And this equation boils down to be this one, if you plug it in our formula. And when beta is minus a half, so this is the case that I showed to you with the nice magical function, right? This is the case Lebesgue measure and x to the 6. So this is when beta is minus a half, gives me Lebesgue measure on one side, and the other side I get 3. But my exponents are 2 alpha and 2 beta plus 1, so I get x to the 6. So this reduces to this equation, and you want to find the smallest root. The smallest root happens to be the root of the numerator here, sine of lambda. So the smallest root is pi. So this is why you find the sharp constant, in this case, Lebesgue measure, and then the other side, x to the 6 times Lebesgue measure. This leads to this inequality. Well, there has to be some renormalization here. In the original case, we were considering functions of exponential type pi, and this is the answer for exponential type 1. So you have to renormalize things to get the constant correct here. 2 applications, and then I will conclude. 2 applications of this result. If you move things from the physical side to the Fourier transform side, this can be used. It's a completely equivalent problem, but it gives us the sharp answer of all sorts of Poincare inequalities for Sobolev functions in the interval. So I can control the L2 norm of the n derivative by the L2 norm of the m derivative, where n and m are integers, and I can find the sharp constant. And this problem is, I mean, when I observed this, I said, well, I'm sure people have studied this problem before, and this can't be new. And in fact, this dates back to Steklov in 1896. He solved the first cases, 1, 0, meaning the function and the first derivative, and the case 2-1, meaning the first derivative bounded by the second derivative. And then just 30 years later, Janet solved the case n+1, n+1n. And just in 2017, that was the first reference that I found solving the general case m and n integer. So this is the case m and n integer, okay? It's a corollary of what we do in the physical side, because in our physical side, we just want the difference between the exponents to be an integer. So my exponents could be pi and pi plus 3. These exponents are n and m integers, of course, and then the difference between two integers is, of course, an integer. But the way I mentioned to you, why is it expected that the answer is a hard determinant? Because in this paper of Petrova in 2017, she obtained the same answer for the Poincaré inequalities, again, as a big determinant, a big solution of a big determinant. Slightly different than ours, but of course, it has to lead to the same answer. But it's also a solution of a big determinant. Anyway, so there's, of course, you can also generalize this from one dimension to several variables. So you can take Sobolev functions in the Sobolev space of the ball of radius r, and we get sharp inequalities. You know, we can put some gradients and some Laplacians. We get the sharp forms of all of these inequalities here as a corollary of our result in the physical side, if you move to the Fourier transform side. So this is the first. I found it nice when I observed that, in some sense, Poincaré inequalities become a consequence of Fourier uncertainty. You know? They are just two faces of the same phenomenon, at least in this L2 case. So you can actually prove Poincaré inequalities coming with techniques from Fourier analysis. And the application too was the problem that I had discussed with my advisor in that stroll to the cemetery, you know, this monotone one delta problem that we remember. The problem was to find a function from Rd to R, which was radial and non-negative of prescribed exponential type, such that at the origin it was at least 1 and the integral was minimum. And if you rephrase the problem and use some radial symmetrization techniques, the solution of this would boil down to an inequality of this type, you know, L2 norm with weight x dx, L2 norm with weight x to the d plus 1 dx for g of exponential type pi. And now we have the technology to actually find the solution when the difference between the exponents is in this case an even integer. It's the difference of the alpha minus beta is an integer, but the exponent, remember, was 2 alpha plus 1 and 2 beta plus 1. So the distance has to be an even integer. So in this case, we can solve it for all even dimensions. So for all even dimensions, I can actually solve this problem, you know, explicitly. The case which seems to be the most innocent one, in dimension 1, we don't have a precise answer, but this problem was numerically studied by Thierry Dimitrov and Quezada Herrera and Mateo Souza, and a paper in the Proceedings of AMS recently. And they arrived at a very precise approximation of the answer, finding the answer to the first 2 digits are correct. The answer is supposed to be 1.27. So they find upper bounds and lower bounds for the constant, but with the precision of 2 digits. Anyway, so I started with the problem. I showed to you the more general version that we ended up solving, but I'll just mention to you that even the most general version for sharp embeddings in Paley-Wiener spaces is actually a byproduct of an even more general version that talks about entire functions in these so-called Debrange spaces. Okay, but this is a conversation that we're going to leave for the next time. If somebody's interested, you can take a look at the paper. But the more general problem is actually we find this infimum of the multiplication by z to the k in the general space of entire functions. So in particular, we would get those Paley-Wiener spaces, but this is part of a more general discussion in complex analysis. Anyway, I will just, I think I will stop here and then we can discuss, and if you have some questions. Thank you very much for your attention. Apologies for not having my camera on. I'm having some technical problems here.
Yeah, that's fine. Thank you, Emanuel. Are there questions from audience?
I'll try to turn my camera.
Yeah, nice.
So I have two simple questions maybe. What does this Hilbert inequality say? And so does it have, what is the motivation of this simple inequality, Hilbert inequality?
What's the motivation of the?
What does Hilbert inequality say first, and what is its motivation? How does it come?
Okay, so do you still see my screen?
Yeah, you could just enlarge it a little bit.
So this is the Hilbert inequality, right?
Yeah. Just enlarge this the screen a little bit, maximize it.
So this is the original Hilbert, and this inequality was originally studied by Hilbert and Schur. So they were interested in finding the let's say the norms of some matrices with some very specific entries, right? What's the largest eigenvalue of a matrix where the entries are 1 over m minus n or 1 over m plus n? So they studied all sorts of bilinear forms with these entries. Now, the motivation for this generalization of Montgomery and Vaughan involves computing, estimates for the Riemann zeta function on the critical line. So if you want to compute let's say, the integral of the modulus of the Riemann zeta function square in the critical line from 0 to t, or the integral of the argument of the Riemann zeta function in the critical line from 0 to t square. This is called the second moment of the Riemann zeta function up to height t. You will need at some point in the proof to use inequalities of this sort, where you have a sequence of coefficients am, an on the top, and in the bottom, you will essentially use this inequality with log m and log n. Okay, and then they proved this more general version, but the first application that they had in mind was with this lambda m and lambda n being log m and log n to apply for these estimates for zeta on the critical line. And then it just became a folkloric problem. They just proposed this. They proved with a constant which was not optimal, but it's believed that this sort of inequality should be possible with this constant pi. But it's an innocent problem, but it's not easy. I think about it from time to time, still unsuccessfully.
Okay. And how do you find these extremizers? What is your method of proof finding that extremizers?
Okay. So I have one slide about this if you want to have a little bit of a look. So as I told you, the conversation, these inequalities here are a particular case of a more general type of inequalities for Paley-Wiener, for this so-called Paley-Wiener spaces. But you can actually put this even in a more general setup of the branch spaces, where you have the branch space is a certain space of entire functions. It's a certain Hilbert space of entire functions with some integrability on the real line. I won't enter into the technical details of defining it, but what you want, imagine that you have a certain Hilbert space of entire functions. Here we are just in the complex plane, one-dimensional real line and one-dimensional complex plane. So imagine that you have a certain Hilbert space of entire functions. Sometimes you can multiply these functions by a power of z. You can multiply your entire function by z squared, and it might fall in the space. It might fall in the space, or it might go out of the space when you multiply by z. So the general question is, you have a Hilbert space of entire functions with a certain norm, and you give me a k. I want to multiply my function to the k, and I want to find the infimum of this thing. So I don't know if this is going to be in the space or not, but if it is, I want to find the infimum of this thing. Okay, so in some sense, it's almost like computing the operator norm of the multiplication by z to the k in a space of entire functions. A little glimpse of the strategy to solve this problem in general. That's what you're asking. In these Hilbert spaces of entire functions, you do have sampling and interpolation in the spirit that you have for the Paley-Wiener spaces. So you can recover a function f by, let's say, some values of f at certain points. And here I am putting cosine, but this is the strategy adapted to the case of the Paley-Wiener space. In general, this would be the A function that defines the de Bruijn space. So you have a reconstruction formula, and if you want to find the function that is just your original f multiplied by z to the k, you would just write the formula for this function, assume it falls in the space, then it would have a reconstruction formula like this, where the function, instead of being f, would be z to the k f. So this would change here. And then you would have some constraints in your problem, in the sense that if the function g is z to the k times f, then g of 0 is 0, g prime of 0 is 0. All the first k minus 1 derivatives at 0 are 0, because you're multiplied by z to the k. You would have to kind of plug this in the formula, take k minus 1 derivatives here, and you would find certain constraints between, you know, the coefficients an, which I'm calling this. Ans are the samplings at the sampling points. And these guys, which in the case of the Paley-Wiener space are the integers plus a half. In the case of the de Bruijn space are general interpolation points. So with some work, you kind of arrive at the constrained optimization problem in little L2. Instead of working in a problem in big L2, you will transform this into a problem of sequences. You will want to find, for sequences belong to a certain space of sequences, the infimum of a certain weighted L2 norm divided by the classical little L2 norm of the sequence with some constraints. So you want to find the infimum of something with some constraints. And this is the beginning, and then you can start to use techniques like calculus of variations and Lagrange multipliers to start and shape your problem and put it into that matrix form that you see at the end. But this is, in a glimpse, the general strategy, to use the interpolation formulas on the space to reduce to a problem in little L2 with some constraints, to apply techniques from calculus of variations and Lagrange multipliers to work on that.
Yeah.
All right.
Any more questions? I just had one small question probably. So in the weighted inequality with the constant one, you had mod x to the power 6 weight.
The power 6, you mean? Sorry,
Yeah.
I didn't.
So in weighted inequality with x to the power 6, the constant is 1.
Yes.
So if you raise powers higher and higher, do you expect the constant to get smaller?
If I raise the power, and that
Yeah.
if the power